All right, let's jump right into this explainer. Today we're going to demystify the absolute marvel of engineering that powers pretty much all the motion in our world. I mean, from the household appliances humming away in your kitchen to those massive industrial machines building our infrastructure, motion is literally everywhere. And we're going to break down the invisible systems that control it all with such crazy precision, electrical drives.
Just think about it for a second. How does an elevator know exactly, and I mean exactly, where to stop so it perfectly aligns with the floor to let you out safely? Or what about a robotic arm on an assembly line, whipping around at high speeds to pick up a tiny, super delicate microchip without crushing it to dust? That is not just basic movement. That's a masterclass in calculated motion control.
And you know what's really wild? The sheer scale of this stuff. On one end, you've got a tiny 5-watt cooling fan quietly keeping your laptop from melting down. And then, way on the other end of the spectrum, you have a massive 5-megawatt electric locomotive dragging thousands of tons of freight across the country. That's a power difference of 1,000,000 to 1. But despite that astronomical gap in scale, they both rely on the exact same underlying engineering system to get the job done.
So let's pin down exactly what we're talking about here. Now, technically, a system controlling motion could be powered by a clunky diesel engine or a steam turbine. But whenever we use an electric motor as the primary muscle to control speed, position, or torque, well, then we are officially dealing with an electrical drive.
To make sense of all this, we're going to run through 5 quick areas. 1. The magic of motion. 2. Anatomy of a drive. 3. The brain and the muscle. 4. The power modulator. And finally, 5. Why go electric?
So part 1, the magic of motion and how motion control is everywhere. Honestly, whether it's your washing machine kicking into high gear for the spin cycle, your AC keeping the room chill, or an EV merging onto the highway, electric drives are the hidden heartbeat of our daily routines.
Moving right along to part 2, anatomy of a drive, the blueprint. Let's pop the hood and deconstruct the universal architecture that governs every single electrical drive out there, from a remote-controlled toy car to a massive steel rolling mill. This brilliantly maps out the whole shebang. We aren't just jamming a motor's plug into a wall socket. It's a completely closed-loop system. We've got the power source, the power modulator, the motor itself, and the load. But critically, we also have a control unit taking in commands and a sensing unit scooping up real-time feedback. You can clearly see how power flows out from the source and gets carefully massaged before it ever even touches the motor.
You can actually trace that main power flow right along a linear path. We kick things off at the power source. Maybe it's your local AC grid or maybe a DC battery. That raw energy feeds into the power modulator, which literally shapes the electricity. Then, that custom-tailored electrical energy drives the motor, which finally spins the mechanical load to do the actual physical work.
Which brings us to part 3, the brain and the muscle, control, sensing, and motors. To really wrap our heads around this system, let's step away from the abstract engineering boxes for a second. Think of this drive like a living organism, complete with a brain, nerves, and muscles, all working in perfect sync. In this biological analogy, the control unit is the brain. It runs on super low voltage, processing your input commands, kind of like you stepping on the gas pedal. The sensing unit, that's the nervous system, constantly sending back crucial, real-time feedback on stuff like motor current and rotational speed. And the motor itself is the muscle, doing all the heavy lifting based on the exact signals the brain sends it.
And just like human muscles are adapted for different sports, engineers have a whole menu of electric muscles to choose from. You've got your traditional DC motors and then highly efficient AC motors, like the famously rugged squirrel cage induction motor. Those things are legendary in heavy industry because they practically never need maintenance. Then you've got the really specialized stuff, like switched reluctance motors. They have a super lightweight rotor with very low inertia, which makes them absolutely perfect for the extreme demands of space applications.
Okay, part 4, the power modulator, the hands of the system. We've arrived at what I honestly think is the unsung hero of the whole setup. If the motor is the muscle, the power modulator is like the hands, or maybe the precision valves of the system, meticulously dialing that energy flow up and down. Its main job is exactly this: grabbing that raw, untamed electricity from the grid or the battery and shaping it so the motor behaves exactly, and I mean exactly, how the mechanical load needs it to. It perfectly matches the power supply to the specific physical demand of that exact millisecond. But look, its job goes way beyond just acting as a fancy speed dial. The power modulator has 4 absolutely critical functions. Yes, it modulates power for speed and torque, but it's also your primary shield. During crazy transient operations, like a sudden start, slamming on the brakes, or throwing it in reverse, it steps in to restrict massive current spikes that would otherwise fry the source or cause a huge voltage drop. On top of that, it converts the energy into a usable format, and it's the thing actively deciding if the motor is pushing forward, which we call motoring, or pulling back, which we call braking.
To actually pull off that kind of energy conversion, the modulator uses some incredibly specific electronic circuits. For instance, if your wall gives you AC, but your motor runs on DC, you use a rectifier. Got fixed DC from a battery, but need variable DC to tweak your speed? That's a chopper. What if you're running off solar-generated DC, but you're powering an AC induction motor? Then you're going to need an inverter. And if you need to warp an AC source into a totally different AC output, you call in the cycloconverters or AC voltage controllers.
Actually building these converters, it takes some serious engineering chops. Engineers use all sorts of clever combinations of power semiconductors, stuff like diodes and thyristors mixed with transformers to build these specific circuits. The whole design hinges entirely on what kind of juice you have available and exactly what your motor needs to swallow to get the job done. All right, bringing it home with part 5. Why go electric? The advantages. With all this extra complexity we just talked about, the sensors, the control units, the fancy power modulators, why do engineers so overwhelmingly prefer electric drives over old-school, purely mechanical engines like diesel or steam? Well, the answer is pretty straightforward. Electrical drives give you a level of unmatched flexible control and raw efficiency that a mechanical engine just can't touch. You can fine-tune both the steady state and the dynamic characteristics so smoothly and precisely that you can satisfy pretty much any load requirement imaginable. The perks are just massive. First off, because we control the speed electrically, you can completely ditch those clunky heavy mechanical gears. They run silently, they don't pump out local pollution, and unlike a freezing cold diesel engine, an electric drive starts instantly and can handle a full load with zero warm-up time. Oh, and they easily handle 4-quadrant operation, meaning they seamlessly flip between driving forward, reversing, and braking in both directions. Plus, thanks to regenerative braking, instead of just wasting energy as heat when you slow down, they actually pump kinetic energy right back into the source. That saves a mind-blowing amount of power. Oh, and you can even design them to work perfectly underwater, or literally inside explosive or radioactive environments. And really, that brings us right to the bleeding edge. When you realize these drives can thrive in extreme environments, it leaves you with a pretty amazing thought. As solar tech gets better at pumping out efficient DC power, and as special lightweight motors, like those switched reluctance ones we mentioned, continue to evolve, how are these exact same fundamental block diagrams going to power humanity's next phase of deep space exploration? It's honestly incredible to think that the exact same principles keeping your laptop cool right now are the very keys to exploring the cosmos.